Everything in the universe moves, shines, burns, and changes because of energy. But energy is not a substance, a particle, or an invisible fuel hidden inside matter. From galaxies and stars to atoms, neutrons, quarks, and quantum fields, its true nature is far stranger and more fundamental than it first appears. Stay until the end as the journey moves from the largest cosmic structures to the deepest known layers of reality. Like the video and subscribe for more calm journeys into the science of the universe. Across the observable universe, energy appears wherever change occurs. It is present in the light that travels between galaxies, in the motion of stars, in the slow expansion of space, and in the gravitational pull that shapes vast clusters of matter. Energy is not seen as a separate substance drifting through the cosmos. It is recognized through effects. A galaxy rotates, a cloud of gas warms, a photon crosses an immense distance, a planet moves along an orbit. Each event reveals a form of energy and a transfer from one part of a system to another. The observable universe is the region from which light has had time to reach Earth since the early history of cosmic expansion. Its visible boundary does not mark an edge in space. It marks a limit in observation. Beyond that limit, light may not yet have arrived. Within the observable region, matter forms a wide web of galaxies, gas dark, matter radiation, and nearly empty space. Energy is distributed across all of these components, though it does not appear in the same form everywhere. Radiation provides one of the clearest signs of cosmic energy. Stars, galaxies, hot gas, and other objects release electromagnetic radiation. This radiation includes visible light radio waves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. These forms differ in wavelength and frequency, but all carry energy. A single packet of electromagnetic radiation is called a photon. Photons can travel through empty space without needing air, water, or any other material medium. Their journeys allow distant regions of the universe to influence detectors, planets, gas clouds, and living systems far away. The oldest light that can be observed directly is the cosmic microwave background. It fills space as a faint field of radiation and comes from an early period when the universe becomes transparent. Before that time, matter and radiation interact so frequently that light cannot travel freely for long distances. As expansion continues and the universe cools, electrons join atomic nuclei, forming neutral atoms. Photons then move more freely. Cosmic expansion stretches their wavelengths over billions of years, leaving a cold background glow that remains measurable in every direction. This ancient radiation carries energy, but its energy decreases as the universe expands. The stretching of wavelength lowers the energy associated with each photon. In an expanding universe, defining a single total energy for all of space is more difficult than defining energy inside a smaller, isolated system. General relativity describes gravity as the curvature of space-time, and cosmic expansion does not always allow a simple global conservation rule. Local conservation remains precise. In any small region, energy and momentum are accounted for according to the laws of physics. Across the entire evolving universe, the meaning of total energy depends on the geometry of space-time and on how the system is defined. Matter also contributes energy through mass and motion. Galaxies move within groups and clusters. Stars orbit galactic centers. gas falls into gravitational wells, collides, compresses and heats. Even when an object seems still, its mass is part of its total energy. Motion adds kinetic energy, while position within a gravitational system affects how energy changes during falling, orbiting, or escape. These forms are not separate materials, they are different ways of describing the state of matter and fields. On the largest scales, gravity organizes cosmic structure. Slight variations in the density of the early universe grow slowly under gravitational attraction. Regions with more matter pull in surrounding material. Over long periods, gas and dark matter gather into filaments, halos, clusters, and galaxies. As matter falls inward, gravitational energy changes into motion and heat. Gas entering a galaxy cluster can reach very high temperatures as particles collide. Much of this gas becomes so hot that it shines strongly in X-rays, revealing energy released during the assembly of enormous structures. Dark matter plays a major role in this organization. Observations indicate that it has gravity, but does not emit, absorb, or reflect light in the ordinary way. Its exact particle nature remains uncertain. Its presence is inferred from the motion of stars and galaxies, gravitational, lensing the growth of cosmic structure, and other measurements. Dark matter contributes to the energy and mass content of the universe, yet the underlying material responsible for it has not been directly identified. A second large-scale component is dark energy, the name given to whatever drives the observed acceleration of cosmic expansion. Measurements of distant supernovae, the cosmic microwave background, and the distribution of galaxies support the conclusion that expansion is accelerating. The simplest model treats dark energy as a constant property of space, often called the cosmological constant. Other models remain possible, but no alternative has gained decisive observational support. It remains uncertain whether dark energy is truly constant, whether it changes slowly, or whether present descriptions of gravity require modification on the largest scales. Energy in the universe, therefore, appears in both familiar and unfamiliar forms. Radiation can be detected directly. Matter can be weighed through gravity and observed through light. Motion can be measured by changes in position and wavelength. Heat can be inferred from the distribution of radiation. Dark matter is known mainly through gravitational effects. Dark energy is known through the changing rate of cosmic expansion. Each case depends on observation, measurement, and a physical model that connects effects with causes. The largest cosmic view does not reveal energy as a hidden material from which everything is built. It reveals energy as a property that belongs to physical systems. A photon has energy. A moving galaxy has energy. A gravitationally bound cluster has energy. Space itself may possess an energy density described by the cosmological constant. These statements describe measurable features of the universe, not a universal fluid stored inside all things. Across billions of light years, energy changes form while physical laws remain consistent. Radiation leaves stars and crosses space. Matter gathers under gravity. Motion becomes heat during collisions. Expanding space stretches light. The observable universe presents an immense record of these changes. Its distant regions show earlier stages of cosmic history, because light takes time to travel. Through that record, energy is understood not as a visible object, but as a stable quantity used to describe what can happen, what has changed, and how different parts of the cosmos remain connected. Light crosses cosmic space as electromagnetic radiation, carrying energy from one region to another without transporting ordinary matter. It moves through the thin gas between stars, through the wider spaces between galaxies, and through regions that contain almost no particles at all. Its passage does not require air or any other material support. Electric and magnetic fields change together as the radiation travels, allowing energy to move across distances that can span millions or billions of light years. A photon is the smallest discrete packet in which electromagnetic radiation is exchanged. Each photon carries an amount of energy that depends on its frequency. Higher frequency radiation carries more energy per photon, while lower frequency radiation carries less. Gamma rays and X-rays occupy the high-energy end of the electromagnetic spectrum. Ultraviolet radiation follows, then visible light, infrared radiation, microwaves, and radio waves. These names divide one continuous spectrum into useful ranges. The underlying phenomenon remains the same throughout. In empty space, every form of electromagnetic radiation travels at the same constant speed. Visible light does not outrun radio waves, and gamma rays do not move faster than infrared radiation. Their different frequencies affect how they interact with matter, but not their speed through a vacuum. This constant speed is close to 300,000 kilometers per second. Even at that rate, cosmic distances make travel times immense. Light from the sun takes a little more than 8 minutes to reach Earth, while light from the nearest large galaxy takes more than 2 million years. As light spreads from the distant source, its energy becomes distributed across a growing area. A star radiates in many directions, and the same emitted power passes through larger spherical regions as distance increases. The light, therefore, appears fainter, even when individual photons retain their energy during an undisturbed journey through static space. This gradual dilution explains why a luminous object can become difficult to detect at great distance. Large telescopes collect more photons by using wider mirrors or antennas, allowing faint radiation to be measured. Cosmic space is not perfectly empty. It contains atoms, molecules, dust grains, charged particles, and background radiation. Light may pass through these materials, or it may be absorbed, scattered, or redirected. A dust grain can absorb visible or ultraviolet radiation and later release the energy as infrared radiation. A free electron can scatter a photon into a new direction. A molecule can absorb only certain energies that match its internal structure. These interactions change the path and distribution of radiant energy. The spaces between stars contain clouds of gas with different temperatures and densities. Some are cold and dark, while others are warm, ionized, and faintly luminous. Ionized gas contains atoms whose electrons have been removed. When electrons later join ions or change energy states, photons are emitted at characteristic wavelengths. These narrow patterns of light act as signatures of particular elements. Hydrogen, oxygen, carbon, and other atoms each produce recognizable spectral features under suitable conditions. Absorption leaves another kind of signature. When broad radiation from a hot source passes through cooler gas, atoms remove photons at selected wavelengths. A spectrum then shows dark lines where energy has been absorbed. The missing energy is not destroyed. It enters the atoms, changes their internal state, and is often emitted again in another direction or at another wavelength. Because these patterns are precise observations of light, reveal the composition, temperature, density, and motion of material that may be far beyond direct reach. Motion changes the observed wavelength of radiation through the Doppler effect. When a light source approaches, its wavelengths are measured as shorter. When it recedes, they are measured as longer. Shorter wavelengths are described as blue-shifted, while longer wavelengths are described as red-shifted. This shift allows astronomers to measure movement along the line of sight. It does not mean that the source changes its original nature. It means that motion alters the way successive wave patterns arrive at the observer. Expansion of the universe also stretches light, though this process is not identical to ordinary motion through space. As space expands during a photon's journey, the wavelength grows with it. The photon is then observed with less energy than when it was emitted. Radiation from very distant galaxies can begin as visible or ultraviolet light and arrive as infrared radiation. This cosmological redshift provides a record of how much the universe expands while the light travels. Light can also be bent without being absorbed. When radiation passes near a massive concentration of matter, curved space-time changes its path. The source may appear shifted, stretched, brightened, or multiplied into several images. This effect is called gravitational lensing. The photons continue along the locally straightest available paths, while the geometry through which they move is curved. Lensing can concentrate radiation into a detector and make otherwise faint sources visible. Not every photon reaches an observer. Some enter stars, planets, or clouds. Some scatter repeatedly until their original direction is lost. Others continue beyond every available detector. Observation, therefore, samples only a small fraction of the energy carried through space. Instruments are built for particular wavelength ranges because no single detector responds equally to all radiation. Radio antennas measure long waves, optical telescopes collect visible light, and specialized observatories detect X-rays or gamma rays. Earth's atmosphere absorbs many wavelengths and allows others to pass. Visible light and parts of the radio spectrum reach the ground efficiently, while much ultraviolet X-ray and gamma-ray radiation is blocked. Space observatories operate above the atmosphere to measure these ranges more clearly. Their detectors convert arriving photon energy into electrical signals which are recorded and analyzed. The resulting data do not reproduce distant objects directly. They measure patterns of energy that have crossed space. Through these journeys, light acts as both a carrier and a record. Its energy can warm matter, ionize atoms, drive chemical changes, and produce measurable currents in detectors. Its wavelength and intensity preserve information about the conditions in which it forms and the materials it encounters. Across cosmic space, radiation moves steadily through darkness, transferring energy while connecting widely separated regions through physical interactions that remain consistent over immense distances. Gravity shapes galaxies and galaxy clusters by guiding matter along the curves of space-time. On the largest bound scales of the universe, stars gas dust. Dark matter and radiation move within structures held together by gravity. The force does not pull through space as an invisible cord. In general relativity, matter and energy influence the geometry of space-time, and that geometry influences how matter and light move. Across a galaxy, this effect appears as rotation, orbit collapse, and long-term stability. A galaxy contains far more than its visible stars. It also includes clouds of gas, fine grains of dust, stellar remnants, magnetic fields, radiation, and a large halo of dark matter. These parts do not remain still. Stars travel around the galactic center. Gas streams through spiral arms, and smaller objects pass through the surrounding halo. Their motion carries kinetic energy, while their positions within the gravitational field contribute to the total energy of the system. In a spiral galaxy, the central region is dense and bright, while a broad disk extends outward. Stars near the center complete their orbits more quickly because their paths are shorter and the gravitational environment is stronger. Farther out, stars still move at unexpectedly high speeds. If visible matter alone supplied the gravity, orbital speeds would decline more sharply with distance. Instead, measurements indicate that unseen mass extends well beyond the luminous disk. This evidence supports the presence of dark matter halos. The exact nature of dark matter remains uncertain, but its gravitational influence is measured in many systems. It affects the rotation of galaxies, the motion of galaxies within clusters, and the bending of light from distant sources. Dark matter does not appear to radiate or absorb light in the ordinary way. It is therefore mapped through its effects, rather than through direct images. Its gravity helps hold galaxies together and provides deep wells into which ordinary matter can gather. Gas moving through a galaxy continually exchanges energy. As clouds fall inward, gravitational potential energy changes into motion. When streams collide, part of that motion becomes heat. Turbulence develops as gas moves at different speeds and in different directions. Some regions cool by emitting radiation, while others remain warm or hot because of compression, collisions, or energetic activity near the galactic center. The balance between heating and cooling influences where dense structures form. Galaxies do not exist in complete isolation. Many belong to groups containing a few large members and numerous smaller ones. Groups themselves may lie within filaments that guide matter toward larger concentrations. Gravity acts across these environments over very long periods. Two galaxies passing near one another can distort each other through tidal forces. These forces arise because gravity is stronger on the near side of an object than on the far side. The difference stretches stars and gas into tails, bridges, and curved streams. When galaxies merge, most individual stars do not collide because the spaces between them are immense. Their paths change instead as the combined gravitational field evolves. Gas clouds are more likely to interact directly. They compress shock, lose ordered motion, and release energy as heat and radiation. The final system may settle into a new form after hundreds of millions of years. During this process, energy is redistributed among orbital motion, random stellar motion, hot gas radiation, and the changing gravitational structure. Galaxy clusters are larger bound systems containing hundreds or thousands of galaxies. Their visible members move through a shared gravitational field dominated by dark matter. Between the galaxies lies an extremely thin gas that can reach temperatures of tens of millions of degrees Celsius. At such temperatures, atoms are ionized and the gas emits strongly in X-rays. This hot material contains a large fraction of the ordinary matter in the cluster. The heat of intracluster gas comes mainly from gravitational assembly. Matter falls towards the growing cluster and gains speed. Gas streams collide and pass through shock waves, converting organized motion into disordered particle motion. Temperature measures this average microscopic motion. The hotter the gas becomes, the faster its particles move on average. The cluster, therefore, stores a large amount of energy in a diffuse medium spread across millions of light years. Galaxies moving through this gas experience resistance. Their own gas can be pushed backward or stripped away, while their stars continue on paths influenced mainly by gravity. This separation changes the future supply of material available within a galaxy. In some clusters, observations reveal long tails of removed gas extending behind moving galaxies. The process transfers energy and matter from individual galaxies into the wider cluster environment. Gravitational lensing provides another view of cluster energy and mass. A massive cluster curves space-time strongly enough to bend light from galaxies far behind it. The background images may appear as arcs, rings, or repeated forms. By measuring these distortions, astronomers reconstruct the distribution of mass in the foreground cluster. The resulting maps often show that most of the mass does not follow the bright gas or visible galaxies exactly again, supporting the existence of dark matter. Colliding clusters offer especially clear evidence. Their galaxies may pass through one another with limited direct interaction, while clouds of hot gas collide slow and separate from the main gravitational mass. Lensing maps can show that much of the mass remains aligned with the galaxies rather than with the slowed gas. Observations of such systems place limits on how strongly dark matter particles can interact with one another, although the particles themselves remain unidentified. Within a stable cluster, gravity and motion exist in a long balance. Galaxies move rapidly, yet their paths remain bound because the cluster contains enough mass. Hot gas presses outward while gravity holds it inward. Small disturbances continue and matter slowly shifts, but the structure can persist for billions of years. Energy does not sit in one location. It is distributed through motion, heat, radiation, mass, and gravitational relationships. Across galaxies and clusters, gravity acts as the main organizer. It gathers matter, accelerates falling. Material bends, light drives collisions, and stores energy in the arrangement of massive bodies. The visible patterns of the cosmos arise from this steady interaction between matter and space-time. Rotation curves hot gas, tidal streams, and lensing arcs all record the same underlying process. Gravity shapes structure by changing motion, and energy tracks every change within the bound cosmic systems. A star holds energy in several connected forms. Gravity pulls its matter inward while hot gas and radiation press outward. The balance between these tendencies allows the star to remain stable for long periods. Inside this balance, energy moves from dense central regions toward the surface, and then escapes into space as light and other forms of radiation. The star does not burn in the ordinary chemical sense. Its energy comes mainly from nuclear reactions that change light atomic nuclei into heavier ones. A star begins as a cloud of gas and dust that contracts under gravity. As the cloud becomes smaller, gravitational potential energy changes into motion and heat. Particles fall inward, collide, and transfer energy among themselves. The central region grows denser and hotter. During this early stage, the forming star shines because contraction releases energy even before sustained nuclear fusion begins. The process continues until the center reaches conditions in which atomic nuclei can interact. Most stars contain hydrogen, the simplest element. A hydrogen nucleus is usually a single proton. Protons carry positive electric charge and repel one another through the electromagnetic interaction. High temperature gives them rapid motion, while high density increases the number of encounters. Quantum mechanics also allows a small probability that two protons pass through the electrical barrier even when their classical motion seems insufficient. This effect is called quantum tunneling. It permits fusion to occur under stellar conditions. In a star like the Sun, hydrogen fusion proceeds mainly through a sequence known as the proton-proton chain. Several steps gradually combine 4 hydrogen nuclei into one helium nucleus. Other particles and radiation are released during the process. The final helium nucleus has slightly less mass than the original hydrogen nuclei taken together. The missing mass appears as energy carried by motion photons and almost massless particles called neutrinos. The total amount of energy remains conserved. Fusion does not occur evenly throughout the star. It is concentrated in the core where temperature and density are greatest. In the Sun, the core occupies only part of the total radius, but it produces nearly all of the star's nuclear energy. Reactions happen individually and on microscopic scales, yet their combined effect supports the entire star. The rate is slow enough for the Sun to remain stable over billions of years. The energy first appears largely as rapid motion of particles and as very energetic photons. Inside the dense core, photons do not travel directly to the surface. They are repeatedly absorbed, scattered, and re-emitted by charged particles. Each interaction changes their direction and often their energy. The path becomes a long random sequence rather than a straight line. During this movement, the radiation gradually shifts toward lower energies while remaining part of the star's thermal environment. In some stellar layers, radiation carries most of the outward energy. This region is called a radiative zone. Energy moves through it as photons interact with matter. The material remains nearly stable against large-scale overturning because temperature and density change in a way that does not strongly drive convection. Although photons move at the speed of light between interactions, their repeated scattering makes the overall outward transfer extremely slow. Farther from the center, in many stars, convection becomes more effective. Convection is the transport of energy by moving matter. Hotter material rises because it is less dense than its surroundings, while cooler material sinks. The flow creates broad circulating patterns. Near the surface of the Sun, convection forms cells that appear as a mottle pattern called granulation. Bright areas mark rising hot gas, and darker boundaries mark cooler sinking material. The outer visible layer of a star is called the photosphere. It is not a solid surface. It is a thin region from which photons can escape with few further interactions. The light leaving this layer forms the visible face of the star. Its color and spectrum depend on temperature, while absorption lines reveal the elements present in the upper layers. The energy that begins in the core finally leaves through this region after a long journey. Above the photosphere, a star can possess a more extended atmosphere. The Sun's atmosphere includes the chromosphere and the corona. The corona reaches temperatures far higher than the visible surface, even though its density is very low. Magnetic activity is closely connected to this heating. Waves, field motions, and releases of magnetic energy appear to contribute, although the exact balance of processes remains an active subject of research. Magnetic fields store and transfer energy throughout stellar atmospheres. They arise from the movement of electrically conducting plasma, a state of matter in which electrons and atomic nuclei move separately. Rotation and convection twist and stretch the fields. When magnetic structures change, energy can be released into surrounding plasma. This activity produces flares, bright regions, loops and streams of charged particles. The energy comes from fields built and reshaped by motion within the star. A star's internal pressure includes several components. Moving particles create gas pressure. Photons contribute radiation pressure. In more massive stars, radiation pressure becomes especially important because their cores are hotter and their energy output is much greater. Gravity strengthens as mass increases and the star requires stronger internal pressure to remain supported. This drives faster fusion and causes massive stars to use their nuclear fuel more quickly than smaller stars. The relationship between gravity and pressure is called hydrostatic equilibrium. At each depth, the inward pull of the material above is balanced by an outward pressure change. This condition does not make the star perfectly motionless. Waves, convection, rotation, and magnetic activity continue. The overall structure remains stable because small changes tend to produce responses that restore the balance. If the core heats slightly, fusion may increase, raising pressure and allowing expansion. Expansion then cools the core and slows the reactions. Energy within a star is therefore not a single hidden substance. It is measured in the motion of particles, the pressure of radiation, the arrangement of magnetic fields, the mass of atomic nuclei, and the gravitational structure of the whole object. Fusion changes nuclear binding and releases energy, while gravity creates the conditions that make fusion possible. The steady outward flow of energy supports the star and produces the light, by which its temperature, composition, motion, and activity become observable. A planet receives and redistributes energy through a set of connected environments. Light arrives from its star particles, move through surrounding space. Gravity guides matter toward the surface and heat escapes from the interior. Their balance helps determine temperature, weather, erosion, circulation, and the long-term condition of the planetary surface. Patterns differ among worlds, while energy accounting remains physically consistent. For a planet near a star, incoming radiation is often the largest external source of energy. The amount received depends mainly on the star's brightness and the planet's distance. A nearby world receives more energy across each square meter than a distant one. Only the side facing the star is illuminated at a given moment, while the rest remains in darkness. Rotation carries regions through alternating periods of heating and cooling. Part of the incoming light is reflected before it can warm the planet. Clouds, ice, dust, rock, and atmospheric particles all reflect different fractions. The overall reflected share is described by albedo. A bright surface with a high albedo returns much of the light to space, while a dark surface absorbs more. The absorbed energy raises the motion of atoms and molecules, increasing temperature. This energy later leaves the planet mainly as infrared radiation. A stable climate requires a long-term balance between absorbed sunlight and outgoing radiation. If a planet absorbs more energy than it releases, it warms. As temperature rises, the planet emits infrared radiation more strongly. If it releases more than it absorbs, it cools. The balance emerges over large regions and long periods from countless exchanges among air, water, land, ice and clouds. An atmosphere changes how energy moves. Gas molecules absorb some wavelengths and allow others to pass. Visible light often reaches the surface efficiently, while gases such as water vapor, carbon dioxide, and methane absorb parts of the outgoing infrared radiation. They then emit infrared energy in several directions. It is called the greenhouse effect and occurs naturally on several planets. The strength of this effect depends on composition, pressure clouds and temperature. On Venus, a dense carbon dioxide atmosphere produces extreme surface warmth. On Mars, the thin atmosphere provides much less insulation. Earth lies between these cases with oceans, clouds, water vapor, carbon dioxide, and changing ice cover, all participating in the energy balance. Observations show that increases in greenhouse gases reduce the rate at which heat escapes from the lower atmosphere, causing the climate system to gain energy. Air also transports energy through motion. Warm air expands, becomes less dense, and tends to rise. Cooler air sinks in its place. Rotation, surface differences, and the shape of continents or mountains guide these flows into winds and circulation cells. Air carries sensible heat, which is energy associated with temperature, and latent heat, which is energy absorbed or released when water changes phase. Evaporation stores energy in water vapor, while condensation releases it into the atmosphere. Clouds influence energy in more than one way. Their bright upper surfaces reflect sunlight, which tends to cool the planet. They also absorb and emit infrared radiation, which can reduce heat loss from below. The net effect depends on cloud height, thickness, droplet size, ice content, and location. Low, thick clouds often reflect strongly, while high, thin clouds can allow much sunlight through and still limit outgoing infrared energy. Oceans absorb a large amount of incoming energy because water has a high heat capacity. This means that a large energy transfer produces only a gradual temperature change. Surface currents carry warm water toward cooler regions and return colder water toward warmer regions. Winds drive much of the upper circulation, while differences in temperature and salt content influence deeper movement. Through these flows, the ocean stores energy and releases it over seasons, years, and longer intervals. Water also redistributes energy through phase changes. Solar heating causes evaporation from seas, lakes, soil, and living surfaces. The fastest molecules escape into the air, carrying energy with them. When vapor condenses into droplets or freezes into ice that's stored energy, returns to the surroundings. Storms draw part of their strength from this transfer. Their winds and rain are expressions of energy moving through water pressure differences and atmospheric circulation. Land responds more quickly than oceans because rock and soil store less heat in their upper layers. During daylight, the surface can warm rapidly. At night, it can cool just as quickly by emitting infrared radiation. Deserts often experience wide temperature changes because dry air and limited clouds allow strong heating by day and rapid heat loss after sunset. Vegetation, moisture, snow, and soil type alter how sunlight is absorbed and how energy moves into the ground. Beneath the surface, planets can retain energy left from formation. Collisions during growth convert motion into heat, while compression raises internal temperature. Radioactive decay also releases energy as unstable atomic nuclei change over time. In rocky planets, internal heat can drive mantle flow volcanism and the movement of crustal plates where conditions permit. This energy reaches the surface through conduction, rising molten material and volcanic gases, although it is usually smaller than absorbed sunlight at the surface. Magnetic environments add another path for energy transfer. A moving electrically conducting interior can generate a planetary magnetic field. This field redirects many charged particles carried by the stellar wind. Some particles become trapped, while others enter near magnetic poles. Their collisions with atmospheric gases produce auroras and transfer energy into the upper atmosphere. Planets without strong global magnetic fields still interact with the stellar wind through their atmospheres and electrically charged upper layers. Meteorites and dust bring smaller but measurable amounts of energy. As objects enter an atmosphere, resistance converts motion into heat light and shock waves. Most small grains slow or vaporize high above the ground. Larger bodies may reach the surface and release energy during impact. Rare large impacts can alter landscapes and climate, but ordinary planetary energy flow remains dominated by steady radiation, circulation, internal heat, and magnetic interaction. Around a planet, energy continually changes location and form. Sunlight becomes warmth, wind evaporation, currents, and stored chemical activity. Interior heat becomes slow rock movement and volcanic release. Charged particles become auroral light and atmospheric heating. The planet remains a connected system in which every layer responds to the gains and losses of energy moving through it. Ordinary matter stores and transfers energy through the motion and arrangement of its particles. A stone, a drop of water, a cloud of air, and a piece of metal all contain atoms and molecules that move, vibrate, collide, and interact. Although the material may appear still, its internal particles remain active. Its changing form can be measured through effects produced within surrounding matter and fields. Kinetic energy is the energy associated with motion. A moving object carries kinetic energy because its mass changes position through space. The amount increases with mass and rises more rapidly as speed increases. When a moving object slows, its kinetic energy does not vanish. It changes form or moves into the surroundings. A sliding block provides a simple example. Friction acts between the block and the surface, reducing the block's ordered motion. The contacting materials deform slightly, and their atoms begin moving in irregular ways. The surface is warm. The original kinetic energy becomes part of the internal energy of the materials. Internal energy is the combined microscopic energy associated with particle motion and interaction inside a system. Temperature describes part of this internal activity. In a gas, higher temperature usually means that particles move faster on average. In liquids and solids, the situation also includes vibrations, rotations, and interactions among neighboring particles. Temperature does not measure the total energy of an object. A large cool lake can contain more internal energy than a small cup of hot water because the lake contains far more matter. Heat is energy transferred because of a temperature difference. It is not a material stored inside an object as a separate substance. When a warm object touches a cooler, one energy moves from the warmer region toward the cooler region. The direction reflects statistical behavior among enormous numbers of particles. Conduction transfers energy through direct interactions within matter. In a metal rod heated at one end, particles near the hot region vibrate more strongly. Electrons in the metal also carry energy through the structure. Collisions and electrical interactions spread the energy toward cooler regions. The atoms do not travel from one end of the rod to the other, yet repeated exchanges allow energy to move. Different materials conduct energy at different rates. Metals often conduct heat well because some electrons can move freely through the solid. Wood, air, and many plastics conduct poorly because energy passes less efficiently through their internal structures. Such materials act as thermal insulators. Insulation does not stop energy transfer completely. It slows conduction, convection, or radiation. Convection moves energy through the bulk motion of fluids. A fluid is a liquid or gas that can flow. When part of a fluid warms, it often expands and becomes less dense. Gravity then allows warmer material to rise while cooler, denser material sinks. This circulation transports internal energy. Boiling water, atmospheric currents, and molten rock within planets all display convection. Radiation provides a third path for thermal transfer. Every object with a temperature above absolute zero emits electromagnetic radiation. Cooler objects emit mostly long-wavelength infrared radiation, while hotter objects emit more energy and shift toward shorter wavelengths. Radiation can cross empty space unlike conduction and convection. A warm surface loses energy by emitting photons even when no air surrounds it. Absolute zero is the lowest possible temperature in the ordinary thermodynamic description. It corresponds to zero on the Kelvin scale. Matter does not become completely motionless there because quantum mechanics allows unavoidable ground state motion. Reaching absolute zero exactly is not physically achievable through a finite sequence of cooling processes. Experiments can approach it closely, producing unusual states in which quantum behavior becomes visible across many particles. The state of matter depends strongly on energy. In a solid, atoms or molecules remain arranged around stable positions, though they vibrate. In a liquid, particles stay close but rearrange and flow. In a gas, they move more freely and spread through available space. Adding energy can melt a solid or vaporize a liquid. Removing energy can condense a gas or freeze a liquid. During a phase change, temperature may remain nearly constant, while energy continues to enter or leave. The transferred energy changes the arrangement of particles rather than their average kinetic motion. Melting separates particles enough for the solid structure to loosen. Vaporization overcomes attractions that keep molecules close in a liquid. This stored change is described as latent heat. Pressure also reflects particle motion and interaction. Gas particles strike the walls of a container, transferring momentum during each collision. The combined effect of countless impacts produces pressure. Heating the gas usually increases the particle's average speed. If the container cannot expand, collisions become more frequent or forceful and pressure rises. If the gas can expand, it may push the surroundings and perform mechanical work. Work is another form of energy transfer. A system performs work when a force moves something through a distance or changes its volume. Expanding gas can lift a piston, converting internal energy into organized motion. Compressing gas transfers energy into it, often raising its temperature. Engines, turbines, muscles, and geological processes all involve exchanges among heatwork, motion, and stored energy. Sound carries energy through organized vibrations in matter. A vibrating surface pushes nearby particles, creating alternating regions of compression and expansion. These disturbances travel through gas, liquid, or solid, while the particles move only small distances around their usual positions. The wave transports energy and momentum. In empty space, sound cannot travel because no material particles are available to pass the disturbance onward. Elastic materials store energy when their shapes change. A stretched spring, compressed gas, or bent branch can return toward its original form and release stored energy as motion. The storage arises from changes in distances and forces among atoms and molecules. If deformation becomes too large, the structure may change permanently, and some energy becomes heat or creates new surfaces through cracking. At the scale of ordinary objects, energy appears as motion, warmth, pressure, vibration, and deformation. At the microscopic scale, these forms arise from particles moving and interacting in vast numbers. Ordered motion can become disordered internal motion, and internal motion can produce organized work under suitable conditions. Matter serves as the system in which these changes occur, while energy remains the measurable property that tracks every transfer and transformation. Chemical energy appears when atoms join separate and rearrange within molecules. A molecule is a group of atoms held together by electromagnetic attraction. The atoms do not contain chemical energy as a liquid or hidden fuel. The energy belongs to the complete arrangement, including the positions of nuclei, the distribution of electrons, and the forces acting among them. When that arrangement changes, energy can move into or out of the surrounding matter. Atoms form bonds because certain shared arrangements have lower energy than the separated particles. A chemical bond is a stable relationship created mainly by the electric attraction between positively charged nuclei and negatively charged electrons. The electrons occupy regions around the nuclei rather than fixed circular paths. Their allowed patterns determine how atoms approach one another and how strongly they remain connected. When two atoms form a bond, the new arrangement often releases energy. The atoms accelerate toward a more stable configuration, and the excess energy passes into motion, vibration, light, or surrounding particles. Breaking the same bond requires energy to be supplied. This does not mean that every reaction releasing energy contains individually weak bonds. The total result depends on all bonds broken and all bonds formed during the entire rearrangement. A chemical reaction begins when particles meet under suitable conditions. Their electron distributions interact, old bonds weaken, and new bonds may develop. Many collisions do not lead to reaction because the particles approach with the wrong orientation or insufficient energy. The minimum energy needed to reach an unstable intermediate arrangement is called activation energy. It forms a barrier between the starting materials and the products. Temperature affects reaction rates because warmer particles move more rapidly on average. Faster motion increases the frequency of collisions and raises the fraction of encounters energetic enough to cross the activation barrier. A warmer system, therefore, often reacts more quickly, although the final energy difference between reactants and products does not depend only on speed. It depends on the molecular structures before and after the reaction. A catalyst changes the path of a reaction and lowers the activation energy without being consumed in the overall process. It provides a sequence of easier intermediate steps. Catalysts do not create energy and they do not alter the final balance between reactants and products. They change how rapidly the system approaches that balance. Metals, mineral surfaces, and biological enzymes can all act as catalysts. Combustion is a familiar chemical process in which a fuel reacts with an oxidizing substance. In many ordinary fires, molecules containing carbon and hydrogen react with oxygen. Bonds in the starting molecules break and new bonds form in carbon dioxide and water. The products occupy a lower energy arrangement, so the difference leaves as molecular motion, infrared radiation, visible light, and heating of nearby material. The first step of combustion still requires activation energy. A spark flame or sufficiently hot surface supplies enough energy to begin the rearrangement. Once the reaction starts released, energy heats neighboring material and allows further reactions to occur. The flame persists only while fuel oxidizer and suitable temperature remain available. When one condition fails, the rate falls and the visible flame disappears. Chemical energy also appears in batteries. A battery separates substances that tend to exchange electrons. When an external conducting path connects its terminals, electrons move through the circuit, while ions move within the battery material. Chemical reactions at the two electrodes maintain this flow. The energy associated with the chemical arrangement becomes electrical energy in the circuit and eventually changes into light motion heat or another useful form. A rechargeable battery reverses much of this process when an external source supplies electrical energy. Electrons and ions are driven back toward a higher energy chemical arrangement. The storage is not perfect because resistance, side reactions, and structural changes convert some energy into heat. Repeated cycles can gradually alter the materials, reducing how much chemical energy can be stored and recovered. Food provides another system of molecular energy transfer. Plants use light to build energy-rich molecules from carbon dioxide and water. The process stores part of the absorbed radiant energy in chemical arrangements. In cells, controlled reactions gradually rearrange these molecules. Energy is transferred into forms that support movement, growth, repair, transport across membranes, and the construction of new substances. Cellular respiration does not release all available energy in a single, uncontrolled event. Enzymes guide molecules through many smaller reactions. Electrons move through organized pathways, and part of the energy helps create a difference in ion concentration across a membrane. That difference then drives the production of adenosine triphosphate, a molecule used for many cellular transfers. The molecule does not act as a permanent energy container. It participates in repeated cycles of formation and breakdown. Solutions create further chemical exchanges. When salt dissolves in water, its ions separate and become surrounded by water molecules. Breaking the crystal arrangement requires energy, while attractions between ions and water release energy. The observed temperature change depends on which contribution is greater. Some dissolving processes warm the solution while others cool it. In both cases, energy is accounted for through changing interactions. Acids and bases also transfer particles and rearrange bonds. An acid can donate a proton under suitable conditions, while a base can accept one. When an acid and base react, the products may form a lower energy arrangement and release heat. The strength of an acid or base describes how readily these transfers occur, not the total amount of substance present. Chemical equilibrium develops when forward and reverse reactions continue at equal average rates. Molecules still collide and rearrange, but the overall proportions remain stable. Changing temperature, pressure, or concentration can shift the equilibrium, because those changes alter the relative energetic and statistical favorability of different arrangements. The system responds without violating energy conservation. Even simple reactions involve immense populations of particles, so measured chemical behavior represents the average outcome of countless events occurring together. At the molecular scale, chemical energy is inseparable from electric forces and quantum structure. It appears in bond formation, electron transfer, molecular vibration, phase behavior, and reaction pathways. Fuels, batteries, food minerals, and living cells all depend on the same underlying principle. Matter changes from one arrangement to another, and energy records the difference between those arrangements while moving through heat, light, electricity, and motion. Electricity and magnetism describe how charged particles and electromagnetic fields interact. A charged object can attract or repel another object across space. A moving charge can create a magnetic effect, while a changing magnetic field can produce an electric effect. These two behaviors belong to one electromagnetic interaction. Energy can be stored in the arrangement of charges and fields carried through circuits and transferred into motion, heat, light, sound, or chemical change. Electric charge comes in two types called positive and negative. Like charges repel while opposite charges attract. Protons carry positive charge, electrons carry negative charge, and neutrons have no overall electric charge. In ordinary matter, positive and negative charges are balanced. A material becomes electrically charged when some electrons move from one object to another, leaving an excess or shortage. Static electricity appears when charge remains separated for a time. Rubbing materials together can transfer electrons between their surfaces. The resulting imbalance creates an electric field around each object. An electric field describes how a charge would be pushed or pulled at each location. The field is not a drawing used for convenience. It is a physical part of the system and can store energy. The energy of separated charges depends on their positions. Pulling opposite charges apart requires work because they attract one another. Pushing like charges closer also requires work because they repel. The supplied energy becomes electric potential energy. If the charges are later allowed to move, that stored energy can become kinetic energy, heat radiation, or other forms. Voltage describes a difference in electric potential between 2 points. It indicates how much energy can be transferred per unit of charge moving between those points. A battery maintains voltage by using chemical reactions to separate charge. A generator maintains voltage by moving conductors through magnetic fields. The voltage does not itself flow. It provides the condition that can drive charge through a suitable path. Electric current is the organized movement of charge. In a metal wire, many electrons are free to move through the structure. When an electric field is established, they gain a small average drift in one direction, even though their individual thermal motion remains rapid and irregular. The influence travels through the circuit much faster than the average drift of any one electron. A complete circuit provides a continuous path for charge movement. When the path is broken, steady current stops. When it is closed, the electric field becomes established through the conducting material, and energy begins moving from the source toward devices in the circuit. The energy is not carried only inside individual electrons. Much of it travels through the electromagnetic field, penetrating the conductors. Resistance limits current and converts electrical energy into internal energy. Electrons moving through a material interact with atoms, defects, and vibrations in the structure. These interactions transfer organized electrical energy into disordered, microscopic motion. The material warms. A heating element uses this process deliberately, while unwanted resistance reduces efficiency in power lines, motors, and electronic devices. Conductors allow charge to move relatively easily. Metals often conduct well because some electrons are not bound to individual atoms. Insulators hold charges more tightly and strongly resist current under conditions. Semiconductors lie between these behaviors. Their conductivity can be controlled by temperature, light-added impurities, or electric fields, making them useful in electronic switches and sensors. A capacitor stores energy by separating charge across two conducting surfaces divided by an insulating region. One surface gains excess electrons while the other develops a shortage. The electric field between them stores energy. When the capacitor is connected to a circuit, charge can move back toward balance, transferring energy rapidly. Capacitors are used where short controlled releases or temporary storage are needed. Magnetic fields arise from moving electric charges and from the magnetic properties of particles. A current in a wire creates a magnetic field around the wire. A loop of current produces a field resembling that of a small bar magnet. In many permanent magnets, the magnetic effects of electrons become partly aligned within regions of the material. Their combined fields create a stable, larger pattern. A magnetic field exerts forces on moving charges and magnetic materials. The force on a moving charge acts sideways relative to its motion and the field direction. Because of this geometry, a magnetic field can bend a particle's path without directly increasing its speed. The particle's kinetic energy may remain constant while its direction changes. When other forces or changing fields are present, energy transfer can still occur. Electric motors convert electrical energy into mechanical motion. Current passes through coils placed within a magnetic field. Forces on the moving charges produce torque, which turns a shaft. The rotating system can drive wheels, fans, pumps, or tools. Some energy becomes heat because of resistance and friction, but the main transfer changes electrical energy into organized motion. Generators reverse this relationship. Mechanical motion turns coils or magnets so that the magnetic environment changes through a conductor. This changing magnetic field produces an electric field and drives current. Turbines powered by moving water, steam, wind, or gas often provide the mechanical input. The generator does not create energy. It changes energy from motion into electrical form. A transformer transfers electrical energy between circuits through changing magnetic fields. Alternating current in one coil produces a changing magnetic field which creates voltage in a nearby coil. Different numbers of turns allow the voltage to increase or decrease. This makes long-distance power transmission more efficient because high voltage permits the same power to travel with lower current and reduced heating losses. Electromagnetic waves form when changing electric and magnetic fields sustain one another and move through space. Radio signals, microwaves, visible light X-rays, and gamma rays all belong to this family. Their frequencies differ, but each carries energy and momentum. Antennas create radio waves by accelerating charges, while receiving antennas absorb part of the passing field and convert it into electrical signals. Electricity and magnetism therefore reveal energy as a property of particles' arrangements and fields. Charge separation stores energy. Current transfers it. Resistance changes it into heat. Magnetic fields guide motion, and changing fields connect generators, motors, transformers, and radiation. Across every device and natural process, electromagnetic energy remains measurable through the work it performs and the changes it produces. Inside ordinary matter, atoms provide a smaller region in which energy appears through the relationship between electrons and atomic nuclei. An atom contains a compact central nucleus surrounded by electrons described by quantum mechanics. The nucleus carries nearly all of the atom's mass, while the electrons occupy regions that extend much farther outward. The atom does not resemble a tiny solar system with particles moving along fixed tracks. Its structure is defined by allowed quantum states, probabilities, electric attraction, and the energy required to change one arrangement into another. The nucleus contains positively charged protons and electrically neutral neutrons. Electrons carry negative charge. The attraction between positive and negative charge holds electrons near the nucleus, while the behavior of quantum particles prevents them from simply falling inward. Each electron is described by a quantum state, which contains information about the possible outcomes of measurements such as energy, position, and angular momentum. The state spreads through space as a probability pattern rather than marking a single classical path. An atom's total energy depends on the arrangement of its electrons and nucleus. When the electrons occupy the lowest available configuration, the atom is in its ground state. This is the most stable state allowed under the surrounding conditions. A higher energy arrangement is called an excited state. Energy must enter the atom for an electron arrangement to become excited. The energy can arrive through a collision, an electric current, heat, or the absorption of a photon. Atomic energies are quantized. This means that only certain values are allowed. An electron cannot normally remain at an energy between two permitted states. When an atom absorbs exactly the right amount of energy, its electron structure can move into a higher state. When the atom returns to a lower state, it releases the difference, often as a photon. The photon's frequency is determined by the energy change. This produces the sharp spectral lines associated with particular elements. Every element has a distinct number of protons in its nucleus. Hydrogen has 1 proton, helium has 2, and each following element adds another. This nuclear charge changes the electric field experienced by the electrons. The allowed energy states therefore differ from one element to another. The resulting patterns of emitted and absorbed light act as atomic signatures. They allow the composition of distant stars, glowing gases, laboratory samples, and planetary atmospheres to be measured. The size of an atom is not set by a hard outer boundary. Electron probability gradually decreases with distance, and neighboring atoms can overlap. A useful atomic size depends on the type of bond, the electron state, and the surrounding material. Even so, most of an atom's volume lies outside the tiny nucleus. This region is not simply empty in the everyday sense. It contains electron fields, electric potential, and measurable probability distributions. Removing an electron from an atom requires ionization energy. The electron must receive enough energy to escape the attraction of the nucleus and become free under the relevant conditions. The required amount depends on the element and on how many electrons have already been removed. Outer electrons are usually easier to remove than inner ones because they are farther from the nucleus and partly shielded by other electrons. An atom that loses electrons becomes a positive ion, while one that gains electrons becomes a negative ion. Ionization occurs in flames, lightning-hot stars, electrical discharges, and high-energy radiation environments. A photon with sufficient energy can remove an electron in a single interaction. A fast-moving particle can also transfer enough energy during a collision. The energy is not destroyed when the electron escapes. It appears in the work required to separate the charges and in the motion of the released electron and the remaining ion. Electrons can also scatter from atoms without becoming bound. During an elastic collision, the total kinetic energy remains the same while directions change. During an inelastic collision, part of the incoming motion excites or ionizes the atom. The scattered particle then leaves with less kinetic energy. These events form the basis of many detectors, imaging methods, and measurements of atomic structure. The nucleus and electrons also share motion. An atomic nucleus is far heavier than an electron, but it does not remain perfectly fixed. Both move around their common center of mass. This slightly changes the allowed energy values. The effect becomes important in precision spectroscopy, where extremely small differences can be measured. Interactions among electrons, nuclear motion, magnetic effects, and relativistic corrections all refine the pattern of atomic energy levels. Atoms respond to external electric and magnetic fields. An electric field can shift electron probability toward one side, creating an induced separation of charge. Stronger fields can alter energy levels or remove electrons. A magnetic field interacts with the magnetic properties associated with electron motion and spin. Spin is an intrinsic quantum property that contributes angular momentum and magnetic behavior. It is not a literal spinning motion of a tiny, solid sphere. These field interactions divide or shift spectral lines by small amounts. Careful measurements reveal magnetic fields in laboratories, stars, and interstellar clouds. Atomic clocks also depend on precisely controlled transitions between quantum states. Their regular frequencies provide stable standards for measuring time. The accuracy comes from the consistency of atomic energy differences under carefully maintained conditions. Heat changes the distribution of atoms among available states. In a hotter gas, collisions occur more often and transfer more energy. A larger fraction of atoms becomes excited or ionized. The emitted spectrum then reflects both composition and temperature. In cooler matter, most atoms remain in lower states and absorption features may dominate when light passes through them. Statistical physics connects these populations with the temperature and density of the material. Because these patterns arise from universal physical laws, the same atomic transition produces the same characteristic energy in distant galaxies and in carefully controlled laboratories on Earth. Within an atom, energy is therefore expressed through electric attraction, quantum states, motion, and interaction with radiation. It does not occupy a small compartment inside the electron or nucleus. It belongs to the complete physical arrangement. Absorption changes that arrangement, emission lowers it, and ionization separates part of it. Atomic structure turns energy into precise measurable patterns that remain the same wherever the same element exists under the same conditions. Electrons occupy quantum states that determine how atoms absorb, release, and store energy. These states are not miniature tracks around the nucleus. They are allowed patterns described by quantum mechanics. The electron remains a particle, yet no single path completely represents its behavior. Its state gives probabilities for measurement outcomes and responses to surrounding forces. The lowest available state has the least energy permitted by the structure of the atom. Higher states require additional energy. An electron enters such a state only when the atom receives an amount that matches the difference between allowed levels. The transfer may come from a photon, a collision, or an applied electric field. If the amount does not fit an available transition, the atom may fail to absorb it. This selectivity gives atomic spectra their sharp and repeatable patterns. A photon absorbed by an atom transfers its energy to the electron system. The photon then ceases to exist as a separate packet, while the atom enters a more energetic arrangement. The excited state usually lasts for a limited time. The atom can return to a lower state by emitting a new photon whose energy equals the difference between the two levels. The emitted photon may travel in any allowed direction, and its frequency reflects the size of the transition. Some excited states decay almost immediately, while others persist longer. A long-lived excited state is called metastable. Quantum rules make certain transitions unlikely, so the electron arrangement remains elevated even though a lower state exists. Lasers use carefully prepared populations of excited atoms or molecules. When one photon triggers an allowed transition, another photon is emitted with matching frequency phase and direction. Repeated stimulated emission creates a narrow, organized beam. Electron states are organized into shells and subshells. These terms describe groups of states with related energies and angular properties. In a simple atom, states with similar structure may share nearly the same energy. In atoms containing many electrons, interactions among the electrons shift and divide the levels. The complete arrangement becomes more complex, but it still follows definite quantum rules. No two electrons in the same atom can occupy exactly the same full quantum state. This principle is called the Pauli exclusion principle. Because electrons have an intrinsic property called spin, two electrons can share the same spatial pattern when their spin states differ. Once the lowest states fill, additional electrons must occupy higher ones. This layered filling determines much of the periodic structure of the elements. The outermost electrons influence chemical behavior most strongly. They are less tightly bound than inner electrons and interact more readily with neighboring atoms. Elements with similar outer electron arrangements often show similar chemical properties. Atoms may share electrons, transfer them, or reorganize their states to reach lower energy configurations. The periodic table reflects these repeating patterns in electron structure. Electron spin does not mean that the particle rotates like a solid object. It is an intrinsic quantum property with fixed measurable values. Spin contributes to magnetic behavior and affects how electrons combine within atoms. In an external magnetic field, states with different spin orientations can have slightly different energies. This separation produces measurable shifts in spectra and allows controlled transitions used in precision instruments. Angular momentum also appears in electron states. It describes a quantized property connected with rotational symmetry rather than a classical orbit. Different angular patterns produce probability distributions with different shapes around the nucleus. Some are concentrated near the center, while others contain regions where the probability becomes very small. These patterns influence bonding magnetism and the way atoms interact with light. Quantum states can combine through superposition. A superposition is a single state built from several allowed possibilities. Before measurement, the electron may not possess one definite value for every observable property. The state instead assigns probabilities to different outcomes. When an interaction produces a measurement, one result is recorded according to those probabilities. Repeated experiments reveal the distribution predicted by the state. Uncertainty is another basic feature of electron behavior. Position and momentum cannot both have perfectly definite values at the same time. Greater precision in one corresponds to greater spread in the other. This is not caused merely by imperfect instruments. It belongs to the structure of quantum theory. The uncertainty relation prevents an electron from resting motionless at one exact point near the nucleus. Confinement raises energy because a narrowly localized electron requires a broad range of momentum. The balance between electric attraction and quantum confinement helps establish the size and stability of the atom. If the electron were forced into a much smaller region, its kinetic contribution would increase strongly. The ground state forms where the complete energy reaches the lowest allowed value. In materials, electron states extend beyond single atoms. When many atoms join in a solid, their individual levels interact and split into enormous numbers of closely spaced states. These states form energy bands. Some bands are filled while others remain partly empty or separated by gaps. The arrangement determines whether the material behaves as a conductor, semiconductor, or insulator. In a conductor, available states allow electrons to change motion under a small electric field. In an insulator, a large energy gap separates occupied states from accessible empty ones so current does not flow easily. A semiconductor has a smaller gap. Heat, light, or added impurity atoms can lift electrons into conducting states and leave mobile vacancies called holes. Electronic devices control these movements to process signals and transfer energy. Electrons in solids can also release energy as light. In a light-emitting diode, electrons and holes combine across an energy gap producing photons. The gap size helps determine the color. In a solar cell, absorbed photons raise electrons into mobile states, allowing an electric field within the material to separate charge and create current. These processes convert energy without changing the basic quantum rules. At this scale, energy appears as the allowed structure of electron states and the transitions between them. It is measured through photons absorbed or emitted currents. Created bonds formed and magnetic responses produced. The electron does not carry a store of energy independent of its surroundings. Its energy belongs to the state formed with nuclei, fields, and other electrons. Quantum mechanics describes that state with precise probabilities, and experiments repeatedly confirm the resulting patterns. Inside the atomic nucleus, energy appears through the forces that hold protons and neutrons together. The nucleus is extremely small compared with the full atom, yet it contains nearly all of the atom's mass. Protons carry positive electric charge and repel one another, while neutrons carry no overall charge. A separate interaction called the strong nuclear interaction overcomes much of the electric repulsion at very short distances and allows stable nuclei to exist. The strong interaction acts differently from gravity or ordinary electric attraction. It is powerful over distances comparable to the size of a nucleus, but its influence falls rapidly outside that range. Protons and neutrons together, called nucleons, attract one another when they are separated by suitable distances. If they are pressed too close, the interaction becomes strongly resistant. This balance helps keep nuclear matter compact rather than allowing it to collapse into a single point. A bound nucleus has less total mass than the separate protons and neutrons from which it forms. The difference is called the mass defect. That missing mass corresponds to binding energy, which is the energy required to separate the nucleus completely into individual nucleons. The energy is not lost. It leaves during formation through radiation and particle motion, and the final bound system remains at a lower total energy. Binding energy differs among nuclei. Light nuclei generally become more tightly bound when they combine, while very heavy nuclei can release energy when they divide. This pattern explains why both fusion and fission can produce usable energy. The most tightly bound nuclei lie near iron and nickel. Reactions that move lighter nuclei toward this region can release energy, and reactions that move very heavy nuclei towards smaller fragments can also release energy. Nuclear fusion joins light nuclei. Because positively charged nuclei repel one another, they must approach closely enough for the strong interaction to act. High temperature increases their motion, and high density increases the number of encounters. Quantum tunneling allows some nuclei to cross the electric barrier even when their classical energy appears too low. Once close enough, they can form a more tightly bound nucleus and release the energy difference. Fusion in stars proceeds through carefully balanced reaction chains. The energy released in each step appears as particle motion, photons, and neutrinos. Some reactions also change a proton into a neutron or a neutron into a proton through the weak interaction. The products remain governed by conservation of electric charge, energy, momentum, and other quantum properties. Each event is microscopic, but immense numbers of reactions produce a steady stellar output. Nuclear fission divides a heavy nucleus into two main fragments, often with additional neutrons and radiation. Certain nuclei can absorb a neutron and become unstable. They deform, split, and release binding energy because the fragments are more tightly bound per nucleon than the original nucleus. The released energy appears mainly as rapid motion of the fragments. Their collisions with surrounding matter then convert that motion into heat. The extra neutrons from fission can enter other suitable nuclei and trigger further events. A self-sustaining sequence is called a chain reaction. In a nuclear reactor, materials and geometry are arranged so that the reaction proceeds at a controlled rate. Heat from fission warms a fluid which can produce steam and drive a turbine. Control systems absorb some neutrons while moderators slow others to energies that make further fission more likely in the chosen fuel. Radioactive decay occurs when an unstable nucleus changes spontaneously toward a more stable arrangement. The exact time of one decay cannot be predicted, but the average behavior of a large population follows a precise statistical pattern. The half-life is the time required for half of the original unstable nuclei in a sample to decay. It can range from tiny fractions of a second to periods longer than the age of the universe. Alpha decay releases a tightly bound group containing 2 protons and 2 neutrons. The daughter nucleus has a lower atomic number and a smaller mass number. Beta decay changes the balance between protons and neutrons through the weak interaction. In one common form, a neutron changes into a proton while an electron and an antineutrino are emitted. In another form, a proton changes into a neutron through related processes. Gamma decay releases a high-energy photon from an excited nucleus. The numbers of protons and neutrons remain unchanged, but the nucleus moves to a lower energy state. Gamma radiation can penetrate matter more deeply than many charged particles because it carries no electric charge. Its energy can still be absorbed through interactions with electrons and nuclei, producing ionization, heating, and secondary particles. Nuclei also possess quantized energy levels. Protons and neutrons occupy allowed nuclear states, and transitions between them produce characteristic radiation. The structure is more complicated than electron states because the strong interaction acts among all nucleons while electric repulsion affects protons. Nuclear models use different approximations to describe collective motion shell arrangements, deformation, and rotation. No single, simple picture captures every nucleus equally well. The ratio of neutrons to protons strongly affects stability. Light, stable nuclei often contain similar numbers of each. Heavier, stable nuclei require more neutrons because neutrons contribute strong attraction without adding electric repulsion. If the balance moves too far from the stable range, radioactive decay becomes likely. Some nuclei near the limits of stability exist only briefly before emitting particles or rearranging. Energy can also enter a nucleus through collisions. Particle accelerators direct protons, electrons, ions, or other particles toward targets. The collision may excite the nucleus, remove nucleons, combine nuclei, or create new unstable isotopes. Detectors measure the resulting particles and radiation. These experiments reveal nucleus sizes, energy levels, reaction probabilities, and the distribution of matter within nuclei. These measurements test the limits of models used to describe densely packed nuclear matter. Inside the nucleus, energy therefore depends on binding particle arrangement, electric repulsion, and the strong and weak interactions. Fusion releases energy by joining light nuclei into more tightly bound forms. Fission releases energy by dividing very heavy nuclei into more stable fragments. Radioactive decay lowers unstable configurations through particle or photon emission. Nuclear energy is not a separate material hidden in the nucleus. It is the measurable difference between one nuclear arrangement and another preserved through every transformation. Mass and energy belong to one connected description of physical systems. Mass is not a substance that sits beside energy as a separate ingredient. It contributes to the total energy of an object, even when the object is not moving as a whole. This stored contribution is called rest energy. It remains present in particles, atoms, nuclei, and larger bodies, and it can change when the internal structure of a system changes. A particle at rest still possesses energy because its mass is part of its physical state. When the particle moves, additional kinetic energy appears. The total energy then includes both rest energy and motion. As speed increases, more energy is required to produce further acceleration. The particle's rest mass does not need to increase in this description. Instead, its total energy and momentum increase while the rest mass remains fixed. The relationship between mass and energy becomes especially clear in reactions. When particles combine into a bound system, the final mass can be smaller than the sum of the original masses. The difference leaves as radiation motion or another transferred form. When a bound system is separated, energy must enter, and the total mass of the separated products can become slightly greater than the mass of the original system. Mass, therefore, reflects all internal forms of energy, including binding. A warm object has slightly more mass than the same object when cooler. Heating increases the internal motion and excitation of its particles, and that added energy contributes to total mass. The difference is extremely small in everyday objects, but it follows the same principle. A compressed spring also has slightly more mass than the relaxed spring because its stored elastic energy contributes to the complete system. Chemical reactions change mass by tiny amounts. When fuel burns, the products and released energy together have exactly the same total energy and momentum as the starting materials. If only the cooled products are weighed after heat and light have escaped, their mass is slightly lower than that of the original fuel and oxygen. The missing mass has left with the transferred energy. Ordinary scales cannot usually detect this difference because chemical energies are small compared with rest energy. Nuclear reactions produce larger fractional changes. When light nuclei fuse, the final nucleus is more tightly bound and has less mass than the separate starting nuclei. The mass difference becomes motion, radiation, and neutrino energy. During fission, a heavy nucleus divides into fragments whose combined rest mass is lower than that of the original nucleus and absorbed neutron. The released difference becomes rapid fragment motion and other emissions. Particle annihilation offers a direct conversion between rest energy and radiation. When a particle meets its corresponding antiparticle, both can disappear as separate particles. Their mass and motion become the energy and momentum of new particles, often photons. Nothing physical is lost. Electric charge and other conserved quantities must still balance, and the final radiation carries the complete energy and momentum of the initial pair. The reverse process can also occur. A sufficiently energetic photon can help create a particle and its antiparticle, usually near another particle, that can absorb recoil momentum. The photon's energy becomes rest energy and motion of the new pair. Energy alone does not create arbitrary matter without constraints. The reaction must preserve charge momentum, angular momentum, and all other conservation laws relevant to the interaction. In particle accelerators, electric fields give charged particles large kinetic energies. When beams collide, part of that motion can become the rest energy of heavier particles. The newly created particles may exist only briefly before decaying into lighter products. Detectors measure the paths, energies, and momenta of these products. By reconstructing the complete event, physicists infer the mass and properties of the short-lived particle. A decay occurs when an unstable particle changes into a set of lower mass products allowed by physical laws. The original rest energy is distributed among the rest masses and motions of the products. If photons or neutrinos are emitted, they carry part of the energy away. The exact distribution can vary from one event to another, but the total remains fixed when every product is included. Neutrinos illustrate the difficulty of complete energy accounting. They interact weakly with matter and can pass through detectors without leaving a signal. Early studies of beta decay appear to show missing energy and momentum. The neutrino is proposed to restore the conservation laws, and later experiments confirm its existence. Its mass is very small, but not zero, as shown by changes among neutrino types during travel. The exact masses remain incompletely determined. Mass also depends on internal motion. A proton is far heavier than the small rest masses of its constituent quarks added together. Most of the proton's mass arises from energy in the strong interaction, including the motion of quarks and the activity of gluon fields. The mass of ordinary matter therefore reflects stored field energy and confined motion, as well as the rest masses of elementary particles. A composite system can have mass even when some constituents have no rest mass. Photons have no rest mass, yet light trapped inside a perfectly reflecting container would increase the total mass of the container system. The photons carry energy and momentum in different directions, and their combined contribution affects the system's inertia and gravity. Removing the light would lower the mass by the corresponding amount. Gravity responds to more than rest mass alone. In general relativity, space-time curvature is influenced by energy, momentum, pressure, and stress. Radiation can therefore contribute to gravity even though individual photons have no rest mass. Hot matter, moving particles, magnetic fields, and vacuum energy also enter the gravitational description. In ordinary conditions, rest mass dominates, but the broader principle remains important in stars and the early universe. This connection remains measurable from heated solids and chemical reactions to nuclear transformations, particle collisions, and gravitational behavior of radiation. Mass and energy are therefore not interchangeable substances passing through a hidden mechanism. They are connected measures of one physical system. Rest mass records part of the system's internal energy structure, while motion and radiation add further contributions. Reactions can redistribute the total among particles, fields, binding, and movement. Every measurable change preserves the full accounting when all products and interactions are included. Modern particle physics describes nature through quantum fields that extend throughout space. A field assigns a physical value or set of values to every location. The electromagnetic field is a familiar example because it can exert forces, store energy, and carry radiation. Quantum field theory combines this field idea with quantum mechanics. In this description, particles appear as discrete excitations of fields rather than as tiny solid objects made from a separate substance. Each known elementary particle is associated with a corresponding field. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks arise from quark fields and neutrinos arise from neutrino fields. These fields remain present even in regions where no particles are detected. A particle appears when a field carries energy in a particular quantized pattern that can move, interact, and produce measurable effects. The word excitation describes a change above the lowest energy condition of a field. A calm surface of water provides only a limited comparison. A wave can move across the water while the water itself remains distributed throughout the region. A quantum field excitation also moves, but it does not behave exactly like an ordinary wave. It can arrive at a detector as a localized event and transfer a discrete amount of energy and momentum. Quantum fields produce both wave-like and particle-like behavior. An electron can spread through space as a probability pattern and form interference, yet a detector records a single interaction at a particular place. A photon can pass through an optical system as a wave-like field pattern, yet it transfers energy in a discrete event. Quantum theory does not require the particle to change from one substance into another. Both behaviors arise from the same underlying state. A field can support different numbers of particles. The electron field may contain no detectable electron, one electron, or many electrons. The electromagnetic field may contain no photons, one photon, or an immense population. Particle number can change during interactions as long as the relevant conservation laws remain satisfied. A photon can be absorbed, two photons can be produced, or a particle and antiparticle can appear when sufficient energy and suitable conditions are present. Antiparticles also arise naturally from quantum fields. The electron field supports electrons and their antiparticles called positrons. They have equal mass and opposite electric charge. When an electron and positron interact, they can annihilate and transfer their energy into photons or other allowed particles. The field remains. Only the pattern of excitation changes. Pair creation reverses the process when energy enters the fields in a form that permits new excitations. Interactions occur because fields are coupled to one another. The electron field interacts with the electromagnetic field because electrons carry electric charge. When an electron emits or absorbs a photon energy, a momentum moves between these fields. Quark fields interact with gluon fields through the strong interaction. Neutrino and electron fields participate in the weak interaction. The allowed couplings determine which processes occur and how likely they are. The Standard Model organizes these fields and interactions. It includes matter fields for quarks and leptons, gauge fields associated with forces and the Higgs field. Quarks form protons, neutrons, and many other short-lived particles. Leptons include electrons, neutrinos, and heavier relatives. Photons carry the electromagnetic interaction. Gluons carry the strong interaction, and the W and Z particles carry the weak interaction. The phrase force carrier describes how some field excitations mediate interactions. It does not mean that tiny objects simply travel back and forth like thrown stones. In calculations, exchanged field excitations represent changes in the interacting quantum fields. Some of these exchanges can appear as detectable particles, while others are internal parts of the mathematical description and cannot be directly observed as free particles. The Higgs field differs from the force fields. It has a non-zero value throughout empty space, and several elementary particles interact with it. This interaction contributes to their rest masses. Particles that couple more strongly to the Higgs field have larger masses from this mechanism. The Higgs boson is an excitation of the Higgs field detected through its decay products in high-energy collisions. The Higgs field does not account for all visible mass. Most of the mass of protons and neutrons comes from energy associated with quark motion and gluon fields inside them. The Higgs mechanism gives quarks their elementary masses, but the strong interaction produces most of the mass of ordinary atomic nuclei. This distinction shows again that mass can arise from field energy and confined dynamics, not only from the mass values of individual constituents. Quantum fields cannot remain perfectly inactive. Their lowest energy state is called the vacuum state. It contains no ordinary particles for a chosen observer, yet it still has quantum structure. Measurable effects can arise from how fields respond to boundaries, acceleration, or strong external conditions. These effects do not imply that empty space is filled with ordinary particles continually appearing as directly observable objects. They reflect the behavior of quantum states and interactions. Field excitations obey different statistical rules. Matter particles, such as electrons and quarks, are fermions. They follow the exclusion principle, preventing identical fermions from occupying the same complete quantum state. Force particles, such as photons and gluons, are bosons. Many identical bosons can occupy the same state. These differences shape atomic structure, lasers solids nuclear matter, and the behavior of matter at extreme temperatures. Particles also carry intrinsic properties defined by their fields. Electric charge determines electromagnetic interaction. Color charge determines strong interaction for quarks and gluons. Spin determines transformation behavior under rotations and influences statistics. Mass affects how energy and momentum relate during motion. These properties are not small labels attached to hidden material spheres. They are consistent features of the field excitations themselves. At this level, energy is not made from particles, and particles are not made from energy, as though energy were a material ingredient. Energy is a measurable property of the fields and their states. A particle is one possible way for a field to possess and transfer energy. Fields can also store energy in extended configurations, interactions, and collective patterns. Quantum field theory describes these possibilities with exceptional accuracy, while presenting matter and radiation as organized excitations within the fields that fill physical space at every scale. The quantum vacuum is the lowest energy state available to a set of fields. It is not identical to absolute nothingness, and it is not an ordinary substance filling space. In quantum field theory, even the lowest state retains structure because field values cannot remain perfectly fixed. Their measurable properties fluctuate. These fluctuations do not usually appear as permanent particles, but they influence how fields respond to boundaries, forces, and changes in motion. A field in its ground state has the least energy allowed under the surrounding conditions. For a simple vibrating system, quantum mechanics prevents both position and motion from becoming exactly zero at the same time. A small residual energy remains. Quantum fields contain many possible modes of vibration, and each mode contributes a ground state amount in the mathematical description. Adding all possible contributions leads to an infinite result, so the calculation requires careful treatment. Only energy differences are measurable in laboratory physics. A constant shift applied to every state does not change particle reactions or forces in non-gravitational physics. Calculations, therefore, compare one arrangement with another and remove quantities that do not affect observable results. This procedure is called renormalization. It does not mean that arbitrary errors are hidden. It defines measurable parameters through experiments and allows predictions to remain finite and precise. One clear example of vacuum structure is the Casimir effect. Two uncharged conducting plates placed extremely close together alter the electromagnetic field modes allowed between them. The field outside the plates has a different set of available modes. The resulting energy difference produces a force. Experiments measure forces consistent with this prediction. The Casimir effect does not provide a simple measurement of an absolute vacuum energy filling all space. It measures a difference between field arrangements created by boundaries. Similar effects appear in atoms, molecules, and materials whenever the allowed quantum states change. The surrounding geometry alters the field configuration, and the change in energy can produce a force or shift, a measurable level. Atomic binding also depends on quantum fields. An electron and nucleus form a lower energy state through electromagnetic attraction. The bound atom has less mass than the separated particles. quantum fluctuations slightly modify the electron's interaction with the electromagnetic field, producing tiny shifts in atomic energy levels. One such correction is the Lamb shift, first measured in hydrogen. Its successful explanation becomes an important test of quantum electrodynamics. Another correction affects the electron's magnetic behavior. Quantum field interactions cause its magnetic moment to differ slightly from the simplest theoretical value. Measurements and calculations agree to extraordinary precision. This agreement shows that vacuum-related field effects have observable consequences. The term vacuum-related does not imply that particles continually emerge as classical objects. It refers to how the lowest quantum state contributes to interactions and probabilities. Binding energy appears whenever interacting fields form a stable configuration. In molecules, electromagnetic fields and electron states produce chemical bonds. In nuclei, the strong interaction binds protons and neutrons. Inside protons, gluon fields confine quarks and contribute most of the proton's mass. In each case, the bound system has a total energy determined by all motion fields and interactions together. A negative binding energy indicates that energy must be supplied to separate the system into free parts. The word negative depends on the chosen reference point. If widely separated particles are assigned zero interaction energy, a stable bound state lies below that level. The complete physical energy remains meaningful through differences, reaction thresholds, and total mass. The sign records stability relative to a defined arrangement. The strong interaction reveals a particularly deep form of binding. Quarks inside protons and neutrons cannot be isolated under ordinary conditions. Pulling quarks apart strengthens the gluon field between them. Continued energy input eventually creates new particle pairs rather than releasing a single free quark. This behavior is called confinement. Observations strongly support it, although a complete mathematical proof for the full theory remains unresolved. Vacuum conditions can also change in the presence of strong fields. A powerful electric field can make particle and anti-particle production possible, converting field energy into matter. This effect is predicted by quantum electrodynamics and is often called the Schwinger effect. Direct observation in a static electric field remains experimentally difficult because the required field strength is extreme. Related processes are studied in intense lasers, heavy ion collisions, and condensed matter systems. Acceleration can alter how a quantum state is described. An observer moving with constant acceleration may associate a thermal spectrum with a state that an inertial observer calls vacuum. This prediction is known as the Unruh effect. It remains difficult to test directly because ordinary accelerations produce temperatures far below easy detection. The result shows that particle content can depend on motion, while the underlying field state follows consistent laws. A related effect occurs near black hole horizons. Quantum fields in curved spacetime lead to Hawking radiation, allowing black holes to lose energy slowly. For known astrophysical black holes, the predicted temperature is extremely low, and direct detection is not currently practical. The theory combines quantum fields with a fixed curved background, but a complete quantum theory of gravity remains unavailable. Vacuum energy becomes most difficult when gravity is included. General relativity allows a constant energy density of empty space to influence cosmic expansion. Observations indicate that the expansion of the universe accelerates, and the simplest explanation uses a cosmological constant. Its measured energy density is extremely small compared with naive estimates from quantum field calculations. This mismatch is called the cosmological constant problem. No accepted solution explains why the observed value is so small and yet not zero. Some approaches propose cancellations among contributions. Others connect the value with unknown symmetries, changing fields, or a broader range of possible physical conditions. None has received decisive experimental support. Observations continue to test whether dark energy remains constant over cosmic time, while present evidence remains consistent with a cosmological constant. At the quantum vacuum level, energy is revealed through differences, constraints, and field responses. Ground states are not featureless, yet they are not reservoirs of freely available power. Vacuum effects can shift atomic levels, create forces between boundaries, and influence behavior in strong fields and curved space-time. Their measurements are precise in limited settings, while their connection to cosmic gravity remains one of the deepest unresolved problems in physics. At the deepest level reached by present physics, energy is understood as a property of a physical system. It is not a substance hidden inside matter, not a fluid flowing between objects, and not a collection of smaller pieces. It is a quantity that describes the capacity of a system to produce change while remaining tied to the laws governing motion fields, particles, and space-time. Energy takes many forms because physical systems can be arranged and can move in many ways. A body can carry kinetic energy through motion. A field can store energy in its configuration. A molecule can possess chemical energy through the arrangement of electrons and nuclei. A nucleus can possess binding energy through the strong interaction. Radiation can carry energy as photons. These descriptions differ, but they belong to one consistent accounting. The conservation of energy means that the total energy of an isolated system remains constant. Energy may move from one part of the system to another, or change from one form to another, but the complete amount does not disappear. A falling object loses gravitational potential energy while gaining kinetic energy. Friction converts organized motion into heat. A battery changes chemical energy into electrical energy. A star changes nuclear binding energy into radiation and particle motion. This conservation law is connected with a deep symmetry of nature. A symmetry is a feature that remains unchanged under the particular transformation. The laws of physics appear to operate in the same way from one moment to the next. This invariance under shifts in time is linked mathematically to energy conservation through a result called Noether's theorem. The theorem shows that conservation laws are not separate rules added to physics. They arise from underlying symmetries. Energy is therefore closely connected with time. In quantum mechanics, the energy of a system determines how its state changes as time passes. A state with a definite energy evolves in a regular way, while a combination of energy states produces changing patterns of probability. In classical mechanics, energy provides a compact description of possible motion. In field theory, energy governs how fields evolve and interact. The meaning of energy always depends on the system being described. A particle can have kinetic energy relative to one observer and a different kinetic energy relative to another. Gravitational potential energy depends on the chosen reference arrangement. Binding energy depends on the comparison between a bound system and separated parts. These differences do not make energy arbitrary. They show that energy is defined within a clear physical framework. Local measurements remain essential. A detector absorbs a photon and registers a specific transfer. A thermometer records changes linked to microscopic motion. A calorimeter measures heat released in a reaction. A particle detector reconstructs energy from tracks and collisions. Each instrument responds to physical effects rather than sensing energy as an independent material. Energy becomes known through the changes it produces in matter and fields. A unit of energy provides a common scale for comparing these effects. The joule measures the same physical quantity. Whether it describes moving machinery, absorbed light, electrical transfer, chemical change, or heat, allowing very different processes to enter one shared account. In relativity, energy and momentum form a connected structure. Different observers may assign different values to energy and momentum, yet they agree on the laws relating them. Rest mass remains an invariant property for an isolated particle, while total energy depends on motion. For systems of many particles and fields, the combined energy and momentum include every internal contribution. Conservation applies to the complete system. Gravity makes the description more subtle. In general relativity, matter and energy shape space-time, and space-time guides motion. Energy, momentum, pressure, and stress all contribute to curvature. In a small region, local conservation is expressed precisely. Across an expanding universe, a single global total may not always be defined in a simple way. This limitation reflects the geometry of space-time rather than a failure of local physical law. Energy also places limits on what processes can occur. A reaction cannot produce final products whose total energy exceeds the available initial energy. A particle cannot be created unless sufficient energy and the required conserved properties are present. An electron cannot enter a forbidden atomic state. A nucleus cannot decay into products that fail to satisfy conservation laws. Energy helps define the boundary between possible and impossible change. At the same time, energy alone does not determine every event. Conservation laws permit many outcomes, while probabilities forces symmetries and quantum rules select among them. Two systems can contain the same total energy and behave differently because their energy is distributed differently. A hot gas, a beam of light, and a moving solid may carry equal amounts while possessing very different structures and future paths. Thermodynamics adds another layer to this meaning. Total energy is conserved, but useful organization can decline. When ordered motion becomes dispersed among countless microscopic degrees of freedom, the energy remains present, yet it becomes harder to direct into work. Entropy describes this spreading of energy and the number of microscopic arrangements compatible with a large-scale state. Energy conservation does not prevent irreversible processes. A warm object cooling in a room transfers energy into the surrounding air walls and radiation. The total remains unchanged, but the energy becomes more evenly distributed. The reverse concentration is not forbidden by energy conservation alone, yet it is overwhelmingly unlikely because far more disordered arrangements are available. The direction of ordinary thermal change emerges from statistics applied to immense numbers of particles. Physics does not currently identify a deeper material from which energy is constructed. Energy is not classified as an elementary particle field atom or substance. It is a property assigned to states of particles and fields. The same field can have different energies depending on its configuration, and the same amount of energy can appear through many different physical arrangements. The question of what energy is made of, therefore, has no answer in terms of smaller ingredients. Present theory treats energy as a fundamental, measurable quantity, connected with time change and symmetry. Its value tracks what a system can do and how it can transform. It remains conserved locally, shifts among forms, contributes to gravity, and constrains every interaction without becoming a separate object of its own. Across the universe, energy remains present wherever matter, radiation fields, and space-time change. It appears in the quiet motion of galaxies, in light crossing empty space, in heat moving through planets, and in the slow reactions inside stars. It appears again within molecules, atoms, nuclei, particles, and quantum fields. At every scale, the forms differ while the accounting remains connected. Energy does not need a shape of its own. It has no surface, color, texture, or separate location. It is known through movement, temperature, light pressure, binding mass, and change. A photon carries it, a field stores it, a molecule releases it, a nucleus redistributes it. A gravitational system exchanges it as matter falls, rises, circles, and settles. Present physics does not describe energy as being made from smaller objects. It describes energy as a measurable property of physical states. The arrangement of a system determines how much energy it has, how that energy can move, and which changes remain possible. Time symmetry supports its conservation, while thermodynamics describes how it spreads through increasingly numerous microscopic arrangements. Some questions remain unresolved. The relation between quantum vacuum energy and cosmic expansion is not fully understood. A complete quantum description of gravity is still absent. The deepest structure of space-time may reveal new principles. Even so, every tested theory continues to treat energy as a central quantity, linking change across scales. The universe grows quieter in this final view. Motion continues. Fields remain, particles interact, and radiation travels onward. Energy passes through each process without becoming a material substance. It remains the steady measure of transformation, connecting the largest cosmic structures with the smallest known physical states.